All right, I think we can go ahead and get started. A couple practical announcements. The talks are scheduled for about 40 minutes with about 15 minutes for discussion, but you're also encouraged to ask questions during the talks. The best way to do that is probably to post to the chat window or the Q&A window, and I'll be watching those, and I think the speakers will also be watching those. And if you're an attendee as compared to a panelist and would like to be upgraded to panelist, just raise your hand and someone will upgrade you. That will let you speak and be seen. And otherwise, oh, the other thing is if you're a panelist and posting to the chat window, it's appreciated if you choose to post to all panelists and attendees. It's not the default setting, but if you do post, it's nice for everyone to be able to see everything. Okay, and without further ado, let me introduce our first speaker very briefly. Is Marijn Heule from Carnegie Mellon. He's a leader in developing SAT solvers. He's well known for several things, including the cube and conquer method, the proof logging method, which I believe he's talking about today. We'll find out. And also he's one of the authors of a 2,000 terabyte math proof for the Pythagorean triples problem, I should say, which is billed as the largest math proof ever. So without further ado, Marijn, please go ahead.
Thanks for the introduction. Yeah, so I do have indeed the dubious honor of constructing the largest math proof ever. But what we all know is that we like to have short proofs instead of long proofs. And in this talk, I actually want to kind of talk with you about how can we make short proofs using SAT solvers. And so this will be the talk of today. And the short proofs, in order to make them, we require strong proof systems. I have been with several co-authors been working on them. I will present some of them and then talk about how to find proofs in these systems. So the outline of this talk is as follows. First, I will have kind of an introduction of proofs of unsatisfiability. This is probably relatively easy to follow. Then there will be some more detailed talks. First, how we want to have proofs beyond resolution because we are aware of the restrictions of resolution. I will talk about new proof systems to do this. And then I will talk about afterwards finding short proofs in these proof systems and then conclude with future work and challenges. As Sam already noted, please, in case something is not clear, interrupt. It's more important that I think things are clear and then I can adjust the things later. So please, as soon as something not clear or you have any other questions, let me know and then I can interact. Now, first, an introduction in the proofs of unsatisfiability. So, as probably all of us know that certifying satisfiability, if there's a claim that the formula is satisfiable, it's very easy to check, right? So we have the formula shown on the slide, X or Y, not X or not Y, and not Y or not Z. I will use this formula throughout the talk, and this is very easy to check, right? We just have a satisfying assignment, X, not Y or Z, and it's easy to check that this is satisfiable. Right? The problem is what to do when it's unsatisfiable. The very naive way would be to build a truth table of 2 to the power n entries, but it's not feasible, especially considering that we are frequently using formulas with millions of variables. And then the question is, can we make proofs that are smaller than 2 to the power n? Yeah, this is typically not the challenge in practice because the formulas are relatively easy, but how can we make really small proofs? So that's kind of the main question of this talk. So what is a proof? So in this talk, what I consider a proof is simply a string that certifies whether a formula is unsatisfied. And the important part here is that the string can be checked in polynomial time, in the size of the string and the formula. But that doesn't mean that we only that still the proofs can be exponentially large in the size of the formula, right? So, but we do want to the checking to be efficient. By far the most common way of doing proofs of unsatisfiability over the last decades has been resolution proofs. And a resolution proof I will consider simply a sequence of clauses C1 to Cm, where every clause is either contained in the formula or produced by the resolution rule. And the resolution rule is the one shown here on the slide. We have a clause containing a literal x, we have a clause containing a literal not x, and we just merge them and remove the complementary pair. If the last clause in the sequence is the empty clause, the one without literals, which by definition is unsatisfiable, then the original formula is unsatisfiable. No? And it's a well-known result that for every unsatisfiable formula, there is a resolution proof. Now, just a small example. So we have the formula shown on top of the slide, and just below it, there is a resolution proof. It's a sequence of clauses, and in this case, I marked the literals that are used for resolution with blue if it's a positive literal and red if it's a negative literal. And frequently, it's more kind of visualized using a resolution tree. So the same string can also be represented by the tree that you see here. And we can quickly check that this is a valid proof by just checking each of the resolution steps. Now, there are some drawbacks. So for many seemingly simple formulas, there are the famous pigeonhole formulas, Chaitin formulas, mutilated chessboards, and so on and so on. These are seemingly simple, but any resolution proof of them is exponential in size of the formula. Many SAT solvers are now adding techniques to kind of solve formulas that have exponentially large resolution proofs, and dedicated techniques that can solve them quickly, and we want to express them kind of succinctly. So we have a compact expression, and ideally we want to kind of have a linear kind of size proof, so linear in the size of the solving time. And since the resolution proofs are exponential, we cannot really use resolution for such proofs. So throughout the rest of the talk, I am going to use this notion of a clausal proof. It is still a sequence of clauses, so a string representing a sequence of clauses. And on the right, we see a formula consisting of 4 clauses. And on the right, we see a proof consisting also of 4 clauses. And what we're going to do is we're going to check whether adding, say, the first clause of the proof to the formula preserves satisfiability. So we're no longer doing only resolution or a series of resolution steps. The only thing what we're considering here is this equivalent symbol, which is satisfiability preserving. And so what we want to do is we want to check whether the addition of the clause is satisfiability preserving, and we can do this in polynomial time. If we can do this for the first clause of the proof, and the second one, and the third one, and the final one is the empty clause, then since the empty clause is unsatisfiable, then by transitivity, the original formula had to be unsatisfied. Yeah, so it's a very similar kind of in nature as the resolution proofs, although we don't check with resolution, and we have this stronger notion of satisfiability equivalence, which I will talk about more on future slides. Yeah, and so what we're want to do is checking so-called redundancy. And what is redundancy is just satisfiability preserving. The formula with and without the clause are either both satisfiable or they're both unsatisfiable. And we want this to be checked efficiently in polynomial time. And so now we're going to look about which kind of clauses can we add by some efficiently checkable redundancy criteria. The most used one or most clauses are actually redundant, can be checked with the following polynomial time procedure, which is known as reverse unit propagation. So probably most of us know what unit propagation is. If we have an assignment that falsifies all literals in a clause except for one, which is unassigned, then we assign the remaining one to true, and we keep doing this until fixed point. The fixed point is either that there are no unit literals anymore, or there is a conflict. And we say that given a formula and a clause, and let alpha be the assignment that assigns all the literals in the clause to false, then C, this clause C, is implied by unit propagation, denoted by what's shown over here, if unit propagation on F reduced by alpha results in a conflict. Now let me briefly show an example. So we have an example formula here with 8 clauses and 4 variables. And now consider the assignment that assigns A to false and B to false. Then this over here becomes a unit clause, and so we're forced to make C true or false. Now this becomes a unit clause, so we're forced to make D false as well. And now this clause is falsified, and so A to false and B to false by unit propagation results in a conflict. Why is this particularly interesting? All the clauses that are learned by CDCL, conflict-driven clause learning solvers, have this property is that they can be checked by reverse unit propagation. So we assign everything in the clause to false, do unit propagation, and it results in a conflict. And also the nice thing is that we can actually produce a resolution proof from this by starting with the falsified clause, as shown here, A or C or D. And then for each of the clauses that became unit, we do resolution. So first we do this with B or C or not D, obtaining A or B or C. And then we do resolution with the other unit clause, A or B or not C. And then we obtain A or B, which is the complement of the assignment. And so the clause learning and CDCL solvers can all be explained by reverse unit propagation. And we can use this unit propagation as a polynomial time procedure to check that the clause A or B is redundant. Okay, so this concludes kind of the introduction. Are there any kind of questions? I think this is probably the easiest part to follow, but still, I wanted to be clear. Yeah. So Emir asked whether a clause is considered redundant if it removes some satisfying assignments, but not all. And the answer is yes. So any clause that preserves satisfiability, so the formula with and without a clause, they are both satisfiable or unsatisfiable, is considered redundant. And that means that if a clause removes all but one of the satisfying assignments, it's still considered redundant. Any other questions?
Marijn, quick question. For an unsatisfiable formula, any clause that you add would preserve unsatisfiability, right?
Right.
So therefore, every clause is redundant.
Yeah, for unsatisfiable formulas, every clause is redundant, but the main question is how can we check this in polynomial time? Right, so this is the thing that, but every clause is redundant. The main question is how can we find clauses for which we can check the redundancy in polynomial time?
If every clause is redundant, why do you have to check it? You can just
because
add it.
otherwise you don't know, because you don't know that the formula is unsatisfiable.
Okay, fair enough. Yeah.
Any other questions? Okay, now let's continue with proof systems that go beyond resolution. First, kind of in the traditional proof systems, everything that is learned or deduced is inferred. And so, for example, we have already seen the resolution rule, and also with modus ponens. If you have C or X and D or not X, we can learn C or D. If we have A and A implies B, we can learn B. And all these inference rules, they reason about the presence of other facts. So if the premises are there, then we can infer the conclusion. With all the proof systems we're going to see from now on, we are doing something different. So we're no longer reasoning about presence, but we're going to reason about absence. And this is required when we kind of want to add clauses that actually remove solutions. So what these proof systems will have is that they only require that we preserve satisfiability. And in order to do this, we need to reason about absence. And this is what we call interference-based proof systems. Why are we calling this interference-based proof systems? Because for a normal formula, we can add a clause C that removes some solutions. Or so if we, for example, we have we can learn a clause, two clauses, and if they're based on presence, then if we can learn them independently, we can add them both at the same time, and we still are fine. However, if we only talk about preserving satisfiability, if we learn two clauses that we could add individually, but one might remove some part of the solution, another one might remove some other part of the solutions, and together they remove all solutions, so we cannot add both at the same time, right? So this is something in which interference-based proof systems differ with inference proof systems. And this might sound new, but actually this reasoning about absence is as old as Satzhoven. If you go back to the early work by Davis and Putnam and Logman and Loveland, they already had the so-called pure literal rule. If a literal not X is not occurring in the formula, then we can learn the unit clause X. And learning this unit clause X might actually remove solutions. Another proof system from the 60s that reasons about absence is the extended resolution proof system. That proof system says that if a variable X does not occur, or as shown on the slide, if the literal X and the literal not X do not occur in the formula, then we can add a definition that defines X based on literals existing in the formula. So, for example, we can add the definition X is the end of literals A and B, and A and B occur in the formula, but X does not occur in the formula. And this could be kind of considered a first interference-based proof system, although it's kind of in between. I will talk about it more later, because you do need to reason about absence, because it's not allowed to add this definition if X is already present. And this proof system is very powerful. Actually, there are no lower bounds known for extended resolution. So just to give an example of the strength of extended resolution, there is this well-known pigeonhole problem. So we ask whether we can put n+1 pigeon in n holes with at most one pigeon per hole. This is clearly not possible, and any child would probably of say 4 years or older would know this if you ask it in this way. But if you translate it into say propositional logic, then all the pigeons in holes get different names, and resolution proofs are exponential in the number of pigeons. But extended resolution proofs are polynomial in size, and they have been constructed by Cook in '67. So extended resolution is very powerful, and there's very short manual proofs. However, there is still no method to find such extended resolution proofs, for example, for the pigeonhole formulas automatically. The reason is that extended resolution allows you to add definitions based on existing variables, but the search space for these definitions is enormous in size, and it's very difficult to come up with effective definitions. So there have been several approaches. For example, pairs of literals that occur frequently in conflict clauses. We add definitions of such pairs. This helps somewhat, but still the proofs are still exponentially large. One of the problems that I think is there is that it's so difficult to compute proofs, to find the right definitions. So can we have strong proof systems without new variables? And the first kind of approach in this direction was the notion of block clauses. Okay, so what's a blocked clause? A blocked clause is a clause is blocked C or X on literal X if all the resolvents are, so all the clauses containing not X are a tautology. Let's consider a small formula, A or B, and A or not B or not C, and not A or C. The first clause is not blocked because if we have, for example, if X is in this case A, we can resolve it with this clause, not A or C, and then we have clause B or C, which is not a tautology. However, A in the second clause, not C in the second clause, and C in the third clause, they are witnesses that the second and the third clause are blocked. And actually, if we remove these clauses, then we can also remove A or B, because then A and B become also witnesses of blockness. And so for this formula, we can actually remove all the clauses and thereby showing it's satisfiable. But what we're interested more in is that we can actually also add block clauses. And notice that we doesn't require X to be a new variable. And the theorem by Coleman is that adding or removing block clauses preserves satisfiability or unsatisfiability, depending on whether you add or remove clauses. So a block clause is a redundant clause. And block clauses generalize the extended resolution rule. So this was the extended resolution rule. And what you can observe here is that X and not X in the first and second and third clause are witnesses that the clauses are blocked. So first, for example, if we add this clause, X is not occurring, so it's clearly blocked. But then if we add afterwards not X or A, then it's blocked because resolving it with this clause results in a tautology, and the same holds for B. So block clauses can simulate extended resolution, but it can also do things because it can also, you can add block clauses that are not using a new variable. The nice thing is that block clause elimination has been a very powerful pre- and in-processing technique. For example, it can simulate many circuit optimization techniques. And the largest math proof ever, what Sambas kind of used in the introduction, actually we remove lots of redundant clauses by block clause elimination, and therefore make the problem much more simple. So arguably the most popular interference-based proof system is DRAT. And I want to mention it here, but I don't want to go too much into detail here. So that's why there's no definition there yet. The most important thing to know about DRAT is that you can efficiently check it, that the clause has this so-called RAT property, which I will talk about later. The clauses are not implied, and that the addition of RAT clauses preserves satisfiability. Also, what DRAT makes different from other proof systems that we discussed so far is that we also allow the deletion of clauses. This was initially done to make proofs more, that we can check them more efficiently, but it introduces new clause addition options as well. Now, although I don't, because I just want to mention the definition, and I try to make it as simple as possible here, just kind of to give you kind of some feeling how it works. So a clause C or X is a RAT clause, or longer resolution asymmetric tautology, on a literal X with respect to a formula F, if for every clause containing the complement, the resolvent C or D is implied by unit propagation. So maybe you recall the reserved unit propagation that we had before. We said everything to false, unit propagation results in a conflict. Now we have something similar here, but this looks much more like the block clause definition. So in the block clause definition, we had everything the same, except that implied by unit propagation was a tautology. So what was implied by a tautology there is now just replaced by implied by unit propagation. So every resolvent, if we assign everything to false, unit propagation results in a conflict. And this is very powerful to express in-processing techniques and so on. I don't want to go further into detail here, but I want you to kind of give you the most popular interference-based proof system, which is also used in the SAT competitions. Now let's look at some other strong proof systems which I will going to use for later on. There's a lot of proof systems have been proposed, and especially in the 60s, there were lots of famous proof systems have been proposed. And a selection has been shown on the slide on the left, and they are shown in increasing strength. So if there's an arrow from one proof system to another one, it's strictly stronger. And what we see here is that we have all these proof systems with extended resolution at the top. And we have here in the middle general resolution, and CDCL finds proofs in this proof system. And so it seems to be kind of in the middle of being of its strength. But also, as we know now, they're very efficient methods to find proofs in general resolution using CDCL. It's my feeling that these proof systems, they're mostly designed with the question of whether there exists a short proof for certain formulas in mind. But I think the more important question for practice is whether we can find short proofs. And so what I've been working on with various co-authors is actually to make proof systems that are generalizations of extended resolution. So the new proof systems, actually extended resolution is at the bottom. And we have these proof systems that are generalizations. So what I mean with the dotted arrow is that every proof in this system is also a proof in this system, but there's polynomial simulations between all of them. And so here we see, for example, the RAT proof system, which I discussed on the prior slide. And here we have a new proof system called set propagation redundancy, which I think is also, again, at a nice sweet spot for finding short proofs in a stronger proof system. And we call this procedure SDCL, which is short for satisfaction-driven clause learning. Okay, I think so. Nicola, let me, because I think this goes, I think this will be a good question to kind of discuss at the end of the talk. And so I kind of want to kind of show late, but I think it's a good point to discuss other proof systems that don't have new variables. Because actually all the proof systems, yeah, oh, sorry?
Actually,
okay, thanks.
Marijn, there's a quick question here. When
Yeah.
you say that these proof systems are strong, you're not saying they're stronger than extended resolution, right? They're all polynomially equivalent to it.
Yes.
Is that fair?
Yeah. But there are generalizations. Like, for example, with the block clauses, we've seen that any block clause proof of any extended resolution proof is a block clause proof, but not any block clause proof is an extended resolution proof. So it generalizes the concepts, and there's a polynomial simulation. Yeah, so that's what the arrow means.
One other question, if I can ask. You have SPR and SDCL on the same line, but they're not the same, are they? Or
I think SDCL is a procedure and SPR.
Yeah, so SDCL is a procedure that finds proofs in the SPR proof system, similar to that CDCL finds proofs in the general resolution proof system.
okay.
Yeah, so they're not the same. This is a decision procedure similar to CDCL for general resolution.
Okay. Is it known whether SDCL simulates extended resolution? Maybe this is.
That's a good question.
So what exactly?
Maybe that's a good thing for after the end of the talk.
Yeah, because every SPR proof is also an extended resolution proof.
I think, Marijn, what Sam is asking is just as it took a while to prove that CDCL is polynomially equivalent to resolution, it's possible that we don't yet have a proof for SDCL is polynomially equivalent to SPR.
Yeah,
you may hope so, but it may not.
Yeah,
even under non-deterministic branching.
Yeah, and the thing here is also that SDCL, as it's currently kind of implementation and proposed, does not introduce any new variables, right? And we don't know the strength of set propagation redundancy if we don't allow new variables, right? So this is all what Sam calls SPR minus. Yeah. But let me also, for the sake of time, continue, and then we can discuss these and other questions later. So I want you to give you kind of some impression of how this kind of works. And I try to make an example that hopefully makes it somewhat clear. And for that, I use the problem of mutilated chessboards. So what's a mutilated chessboard? So we have a chessboard and we take away two opposite corner cells, and then we ask whether the remaining chessboard can be filled by dominoes, which cover two squares each. The question is clearly no. Why? Two opposite corner cells of any chessboard have the same color. If we take them away, then one color occurs more frequently than the other color. Every domino covers one white and one black cell, and so clearly we cannot do this. However, for automated reasoning techniques such as SAT, this is an extremely hard problem because it is not aware of this nice chessboard pattern, and it's not aware that one color occurs more frequently than the other one. Now let's have a look what proof systems are doing with this. So consider that we have a solver that produces the assignment shown on the right here, and what happens in the general learning technique. So what we see here on the left is actually what a CDCL solver would do in this situation. So it's able so we had 30 dominoes placed. We have an assignment with 30 dominoes. Now there's a conflict, and it is able to simplify it to an assignment with 14 dominoes. And that's actually the 14 dominoes shown on the slide. So CDCL gets us from 30 dominoes to 14. So it's an improvement, but it's still, if you have a larger board, this will still result in exponentially large proofs. The interesting thing, what the new proof systems allow you to do is, and it's actually also what we observed in practice when we implemented this, is that if you give the same assignment to the SDCL, which I haven't described yet, and I will only do later to some degree, but the important thing here is that SDCL can give you back just 2 dominoes. And actually it gives you back these 2 dominoes. And so what is actually going on here? So what the new proof systems allow you to do is that, assuming that we can cover the entire grid, and there are 2 horizontal dominoes on top of each other, then we can also cover the entire grid where these 2 horizontal dominoes are replaced by 2 vertical ones. So without loss of generality, we can say that there is no 2 dominoes at that spot, 2 horizontal dominoes on that spot, and we can add it as a clause. And this is what the procedure will give you. There's a lot of details going on here, and I just want to give you the high-level picture here. But the proof system allows you to actually learn this binary clause instead of this clause of length 14. And more in general, so what the proof system is actually allowing you to do is that as soon as you see 2 horizontal dominoes on top of each other, it says, okay, I can block this because then I can replace it by 2 vertical dominoes on the same location. And we can do this over the entire board of the board. Additionally, if we have 2 vertical dominoes next to each other with a horizontal one on top, then we can replace it by 2 vertical ones next to each other with a horizontal one below it. If both of these patterns are blocked over the entire grid, then the number of possible assignments goes from exponential to linear, and the CDCL solver will quickly be able to refute those linear remaining positions. So by adding these binary ternary clauses, we can actually have linear size proofs for mutilated chessboards. So this is a very high level kind of description. I will come next slides go into more detail, but are there any questions at this point? Okay, in that case, let me continue. So this was kind of an overview of these proof systems that go beyond resolution. I will go into some more detail in the next section. Actually, I wanted to make this kind of clear with something that we discussed earlier in the workshop, is autarkies. So what is an autarky? An autarky is a non-empty assignment such that every clause that is touched by the assignment is also satisfied by the assignment. Yeah? And kind of the easiest autarkies are pure literals and satisfying assignments. And so consider we have this formula over here. That was the one on the earlier slide. A pure literal is not C over here, so that's an autarky. And this is the satisfying assignment that we have is also an autarky. We're mostly interested in autarkies that are not of this, somewhere in between them, pure literals and satisfying assignment, but they hardly occur, say, in the wild. And the nice theorem about autarkies is that if we have an autarky for formula F, then the formula F and F alpha are satisfiability equivalent. So again, autarkies hardly happen in practice, but what does happen a lot in practice is the so-called notion of conditional autarkies. So we now have an assignment that consists of two parts, a conditional part and an autarky part. And an assignment is called the conditional autarky for formula F if the autarky part is a non-empty autarky for the conditional part. Again, we have our formula over here. And let X be the conditional part and not Y be the autarky part. And so the conditional autarky is X or not Y. And this is a conditional autarky for F if, because, so this is the formula under the condition. So it removes both the clauses containing X, and Y is now satisfying, not Y is satisfying this, the remaining clause. And although autarkies hardly occur, conditional autarkies you encounter all the time. Now, how can we use this? So, given a conditional autarky for formula F, what we can do is we can add the following constraint to the formula that the condition implies the autarky. Yeah? So we negate everything here. So we negate everything in the condition, and then for each of the literals in the autarky, we can add a clause. And so in the above example, we will learn not X, X implies Y, which is the clause not X or not Y. Now, what's the relationship of what we have been talking about before? So first, in order to see this, is the key thing that actually will be used in SDCL is the so-called positive reduct. So the positive reduct is a formula based on another formula. So we have a formula F and an assignment alpha. And the positive reduct is a formula that contains the complement of the assignment. So all the literals negated. And from all the clauses in the formula that are satisfied by the assignment, it contains only the literals that are assigned by the assignment. So let me give two examples to kind of make it a bit more clear. So we have our formula that we have been using throughout this talk. And so let the first assignment be just assigning X to true. So then the clause will be not X. And so this is not X over here. And from these two clauses, we only use the assigned literals, which in both cases is just X. So we have two unit clauses, and this formula is unsatisfied. Now consider a second assignment, X and Y. So the clause will be not X or not Y. The positive reduct will be not X or not Y, which is clause C2. And from the formula, the variables that have been assigned. And this is X or Y and X or not Y. And this formula is satisfiable. And now, without going into too much detail, but the important thing here is that given a formula and assignment, every satisfying assignment of a positive reduct is a conditional autarky. And so so there's a lot of things that kind of I cannot go into detail here, but we can use this assignment. So if we use kind of what I've shown here on this slide, the clause not X or not Y, if we add this clause to the formula, it would actually block this assignment. So what I'm going to tell a little bit more, but in short detail, a little detail is if we have this assignment alpha and we construct a positive reduct and it's satisfiable, we can add a clause that blocks the current assignment. And so this is how we're going to use this. Now, let me show you how this satisfaction-driven clause learning works on a very high level. So first, what is CDCL? Most of us probably have seen this now at some point. CDCL, what does it do? It picks a variable, assigns it to a true value, simplifies the formula, and it does this until you hit a conflict. So this is the main loop, which kind of uses 90% of the runtime. Only at that point, the reasoning starts to kick in, and we add a clause that blocks the current assignment. And then we kind of start over. What is going on in SDCL is it's very similar to CDCL, except the one over here. So in every current assignment that we have in the formula, we ask whether there is another state that is at least as satisfiable. And in our case, we actually ask this question by running the positive reduct. Is the positive reduct of the formula and the current assignment satisfying? If that's the case, and notice that this is an NP complete check because we just constructed a new satisfiability formula, then we block the current assignment and we continue. Yeah, so sorry that because of kind of the limited time, I only describe it on this high level, but we use conditional autarky reasoning to block things, and this actually gets us so-called SPR clauses. And this procedure is able to get us very short proofs for the pigeonhole formulas. It's able to get us short proofs for the Chaitin formulas. Mutilated chessboards, it really depends a bit on the size. It's not completely working for all sizes yet. But for example, for the pigeonhole formulas, we only find proofs that use only binary and unit clauses. And so we can use this procedure to use this reasoning to get very short proofs for these hard formulas. Okay, let me kind of conclude, and then we can take questions. Yes, so Paul Beam asked so if you have a satisfying assignment, can you know which part is the autarky? Yeah, so everything that is common with alpha will be the conditional part, and everything which is not common with alpha is the autarky part. So what's the future? So let me only focus on these points. We have now not only these new proof systems, we also have verified checkers for these proof systems. And the nice thing is what we can have now, what I also heard from solver developers, is that we can they don't care too much about correctness or completeness of the solvers, but they just produce the proofs, and it allows them to make solvers more complex and more efficient because we can easily check whether the reasoning is correct. And so we can have now these very complex and efficient tools while having full confidence in the results. The verified proofs are now in different theorem proving systems, including ACL2, Isabelle, Kok, and KML. And also what I think is very nice is that these checkers are actually used in industry as well. So before I actually have the last part of the talk is actually only already some questions. I didn't were able to talk too much about the proof systems here, but can we find lower bounds for proof systems if they don't have new variables? And I think one of the interesting open questions is, what is the power of conditional autarky reasoning? Can we also simulate without new variables other of the kind of classical proof systems, including Frege and cutting planes? And can we design even stronger proof systems? Sam also, in his paper with Neil, actually has this substitution redundancy, which is actually a generalization of propagation redundancy. Yeah, so can we even make stronger ones? And on the practical side, there's also lots of open questions. Which are good heuristics? How can we make the clauses that we learned using SDCL as small as possible? Can we do something stronger than the positive redux? Can we use local search? And constructing the positive redux is currently quite costly. How can we do this more cheap? So these are just kind of questions. I'm happy to talk about any of them. But maybe there are some other questions from the audience that are more kind of interesting. So this concludes my talk, and I'm happy to go into answering questions.
Thank you very much. I'll wave my hands as if clapping for everyone. So a very, very nice talk. And we have some time left for questions. So there's a couple in the chat window. So why don't we start with those? Amir asks, is there a connection between proof systems and symmetry breaking?
To some extent there. So I think, so with symmetry breaking, what we have is, so if we have a solution maps onto another solution by symmetry, then the proof systems allow you to kind of to break it, to express the symmetry breaking. But I think that the proof systems are stronger. So what I think on a very high level is that if you add a clause, if you can say that, for example, for a certain assignment, if there's another assignment that is at least as satisfiable. For symmetry breaking, it is that you have one satisfying assignment and there's another branch with another satisfying assignment, and then you can block it. But in principle, this would be stronger because this branch might not have a satisfying assignment, and you can still block it because reasoning allows you to say, okay, there's another one that is more satisfiable, and that one might have a solution. So for symmetries, it's symmetric, right? There's a solution here, solution there. For these proof system, it's not necessarily that the one that you're kind of blocking is actually has a solution. So it's frequently. So one of the powers is that you can do symmetry breaking, which allows you to, for example, have quick refutations, for example, for the pigeonhole. But these proof systems are stronger, and that they can do things I think that symmetries cannot do.
Good. And Fahim has a question.
Yeah, so Marijn, could you clarify briefly the relationship between the block clause elimination and extended resolution? So I could certainly see that the extended resolution clauses are blocked clauses.
Yeah.
But how would you simulate a proof in extended resolution with block clauses? That I didn't understand.
So as soon as you have, so the proof of extended resolution of block clauses is simply you add these clauses. So you as soon as you want to introduce the definition, instead of introducing the definition in some way, you just add the clauses as redundant clauses to your formula.
Okay.
Oh,
I see. Okay.
Yeah. So it's just because in these clausal proof systems, just everything is reduced to the addition and removal of clauses. And when extended resolution decides to add a definition, you just add the block clauses.
Okay, I see.
Okay. Karam has a question. Oh, it's a comment on symmetry. Mutilated chessboard is fully symmetric. I think adding high-level symmetry info should solve it for any size, he writes.
Let me see. So that I would actually be very interested to see how you would do this symmetry breaking. But so the clauses that actually are kind of added here, right? You could see them as kind of some form of symmetry breaking. But I'm not sure whether I tried this, but I don't think that existing symmetry breaking techniques actually solve them efficiently.
Not existing symmetry breaking, Marijn. What I'm thinking of is when you mentioned introducing variables, that actually takes advantage of some structure in the formula. The formula has some structure to it, the hierarchical decomposition of the formula. Symmetry is also another part of structure. I think just adding kind of some additional info about the structure of the formula. And in the reason that symmetry breaking didn't work in general is because the formulas that we apply symmetry breaking to are not fully symmetric. And finding the symmetries, does not sometimes work. The symmetry breaking predicates do not work with the CDCL procedure. But if you know that all of the cells in the chessboard are symmetric, all of the tiles are symmetric, I haven't done it, but I think you can add some global constraint that basically not just eliminates, not maps solutions to solutions, but also maps non-solutions to non-solutions.
But so Armin also mentioned and that's a correct observation from Armin, is that the CNF is not symmetric, right? And so
that's what I'm saying is if the CNF is not symmetric, that means the formula itself is not symmetric, but the actual function describing the board is fully symmetric. So the syntactic symmetry is not full, but the semantic symmetry is full.
Yeah, but I think it would be a nice challenge to kind of come up with some symmetry breaking techniques for this problem, right? But I think the nice thing about the new proof systems is actually that it comes up with this domino argument automatically. When we run the solver for the first time, it actually gave us these patterns. And I think the important thing is that we can find such arguments automatically. And because of course, if you write this as with cardinalities, then you can solve it instantly, right? Because it's the number of white is larger than the number of black. So of course,
what I'm confused about is why is it working for pigeonholes and not for this? Because the same argument should hold, right?
Yeah, but the reason is that because of the because the pigeonhole are fully symmetric. Also, the solver kind of does a more symmetric search than for the mutilated chessboards, and so with the right heuristics it will be able to find them, but we don't have these heuristics yet.
Okay, thanks.
Let's do one last question from Paul. He asks, does SPR use clause deletion also?
So we have a proof. So the proof system that kind of I talked about, I talked only about the clause addition aspect, but all of the proof systems that we're using in practice combine both clause addition and clause deletion. So also we have this kind of DSPR proof format, which combines it. So I think the short mutilated chessboards I have, they don't require deletion, and there are no clause deletion steps, but they can easily be combined. Is that your question?
Yes, thanks, because you had only mentioned the clause addition.
Yeah, because clause addition is the only thing that's required, but I think in practice you want to have proof systems that also support the deletion.
Okay. All right. There's another comment from Paul about the symmetries for mutilated chessboard are only rotational since the distance from corners breaks symmetries. I think we've already covered that. So if there's no other quick questions, I think we're running a little over on time, so maybe it's time to move on. Thank you again very much for the very interesting talk. And
thank you.